What specific problem does the TIM method aim to solve in the context of long-horizon reasoning and multi-agent architectures?
The TIM method aims to address the limitations of traditional large language models, LLMs, in handling long-horizon reasoning and the complexities of multi-agent architectures. Specifically, it seeks to overcome the constraints imposed by fixed context windows and the inefficiencies of managing multiple agents, which often require extensive handcrafted context management and coordination. By modeling reasoning trajectories as recursive trees of subtasks, TIM allows for selective pruning of irrelevant subtasks, enabling the model to focus on a dynamic working memory that enhances contextual awareness without being bogged down by unnecessary information. This approach not only facilitates virtually unlimited long-horizon reasoning, but also streamlines the integration of external tools, reducing the overhead associated with interagent communication and tool response processing. Ultimately, TIM enhances the efficiency and effectiveness of complex workflows by enabling a single model inference call to manage intricate tasks seamlessly.
How does the proposed TIM algorithm work? Please illustrate the algorithm step by step, including how it handles subtask decomposition and pruning.
The TIM algorithm operates by modeling reasoning trajectories as recursive subtask trees, where each task is broken down into simpler subtasks until reaching a leaf node that can be completed in one step. The process begins with a task that includes a thought process, optional tool use, a list of subtasks, and a conclusion. As the algorithm progresses, it spawns subtasks if multi-step reasoning is required, while the details of these subtasks are hidden from subsequent steps to maintain efficient context management. Subtask pruning is implemented through a fixed-size stack that retains only the most relevant subtasks, allowing the model to discard unnecessary details from previous steps. When the stack exceeds a certain threshold, the earliest subtask list is pruned, ensuring that the model only focuses on the outputs of tasks at the same or higher level of abstraction. This pruning mechanism enables TIM to maintain a dynamic working memory, facilitating long-horizon reasoning while optimizing memory usage and computational efficiency. Overall, TIM's structured reasoning and pruning approach allows it to efficiently manage context and enhance performance in complex workflows.
Can you provide a simple example to demonstrate the inner workings of the TIM algorithm, especially focusing on how it manages a recursive subtask tree?
The TIM algorithm manages a recursive subtask tree by structuring reasoning into a hierarchy of tasks, where each task can spawn subtasks as needed. For example, consider a task to organize a birthday party. This task can be broken down into subtasks such as choose a venue, create a guest list, and plan the menu. Each of these subtasks can further decompose into simpler tasks like research venues or select a cake type. TIM utilizes a pruning mechanism to retain only the relevant outputs from prior tasks at the same or higher level of abstraction, discarding unnecessary details from lower-level subtasks. This allows the model to focus on the current task without being bogged down by irrelevant information, thus enabling efficient long-horizon reasoning while maintaining a concise working memory.
What are the theoretical or practical advantages of using the TIM method over standard architectures like transformers or RNNs in terms of memory efficiency and reasoning accuracy?
The TIM method offers significant theoretical and practical advantages over standard architectures like transformers and RNNs, particularly in memory efficiency and reasoning accuracy. Firstly, TIM employs a recursive tree structure for reasoning trajectories, allowing it to prune irrelevant subtasks and focus on a selective working memory, which reduces the number of context tokens and KV cache entries needed during reasoning. This pruning mechanism enables virtually unlimited long-horizon reasoning while maintaining awareness of essential instructions, leading to higher decoding throughput and reduced memory costs compared to the linear token processing of transformers and the constraints of RNNs. Secondly, TIMRUN, the inference engine for TIM, dynamically manages memory by releasing KV states of completed subtasks, which enhances memory efficiency without incurring additional computational overhead. Empirical results indicate that this approach not only maintains reasoning accuracy, but can also improve it by reducing hallucinations, demonstrating that TIM's structured reasoning can outperform traditional models in complex tasks. Overall, TIM's design allows for more efficient tool use and context management, streamlining the reasoning process and enhancing performance in multi-hop tasks.
How has the TIM method been validated or tested in the experiments, and what specific metrics or benchmarks were employed to assess its performance?
The TIM method has been validated through a series of experiments that assessed its performance on various benchmarks, including Math 500, MMLU STEM 500, AMC 2022, AMC 2023, AMY 2024, and GPQA Diamond, which evaluate STEM knowledge and reasoning abilities. The experiments compared TIM's reasoning accuracy against different serving infrastructures, specifically contrasting TIM with TIMRUN, which incorporates subtask pruning and memory management. Key metrics included the maximum KV cache length observed during generation, where TIM achieved performance while using less than half the cache slots required for the full output sequence. Additionally, TIM was evaluated on agentic research tasks using benchmarks like BrowseComp and DataCommons QA, demonstrating its efficiency in eliminating the need for complex agent workflows and task-specific prompts. The results indicated that TIM's structured output and subtask pruning not only maintained high throughput, but also improved reasoning accuracy by retaining only the most relevant information in the KV cache.
What limitations or potential drawbacks does the TIM method face, particularly in relation to computational overhead or generalizability in different application scenarios?
The TIM method faces several limitations and potential drawbacks, particularly concerning computational overhead and generalizability. Firstly, while TIMRUN's subtask pruning mechanism aims to enhance efficiency, experiments indicated that the overhead introduced by memory management can sometimes outweigh the benefits of a shorter KV cache, leading to reduced throughput in certain scenarios. Additionally, the reliance on a structured reasoning format may limit TIM's adaptability to diverse tasks that do not fit neatly into the recursive subtask tree model, potentially affecting its generalizability across various application scenarios. Furthermore, the quality of the synthetic dataset used for training raises concerns about the model's performance on real-world tasks, as the dataset's noisiness could hinder the model's ability to generalize effectively. Lastly, while TIM can handle multi-hop tool use efficiently, the complexity of integrating various tools and managing their responses may still introduce challenges in more arbitrary or less structured tasks.